In mathematics, E8 is any of several closely related exceptional simple Lie groups, linear algebraic groups or Lie algebras of dimension 248. The same notation is used for the corresponding Roots lattice, which has rank 8. The designation E8 comes from the Cartan killing classification of the complex simple Lie algebras, which fall into four infinite series labeled N, Bn, Cn, Dn, and five exceptional cases labeled E6, E7, E8, F4, and G2. The E8 algebra is the largest and most complicated of these exceptional cases. Wilhelm Killing discovered the complex Lie algebra E8 during his classification of simple compact Lie algebras, though he did not prove its existence, which was first shown by Elie Cartan. Cartan determined that a complex simple Lie algebra of type E8 admits three real forms. Each of them gives rise to a simple Lie group of dimension 248, exactly one of which is compact. Chevalier introduced algebraic groups and Lie algebras of type E8 over other fields. For example, in the case of finite fields, they lead to an infinite family of finite simple groups of Lie type. Basic description: the Lie group E8 has dimension 248. Its rank, which is the dimension of its maximal torus, is 8. This is the 8 in eightfold way. Therefore the vectors of the root system are in 8-dimensional Euclidean space. They are described explicitly later in this article. The Weyl group of E8, which is the group of symmetries of the maximal torus which are induced by conjugations in the whole group, has order 21,435,527 equals 696,729,600. The compact group E8 is unique among simple compact Lie groups in that its non-trivial representation of smallest dimension is the adjoint representation acting on the Lie algebra E8 itself. It is also the unique one which has the following four properties: trivial center, compact, simply connected, and simply laced. There is a Lie algebraic for every integer n3, which is infinite dimensional if k is greater than 8. Real and complex forms. There is a unique complex Lie algebra of type E8, corresponding to a complex group of complex dimension 248. The complex Lie group E8 of complex dimension 248 can be considered as a simple real Lie group of real dimension 496. This is simply connected, has maximal compact subgroup, the compact form of E8, and has an outer automorphism group of order 2 generated by complex conjugation, as well as the complex Lie group of type E8. There are three real forms of the Lie algebra, three real forms of the group with trivial center, all of real dimension 248, as follows. The compact form, which is simply connected and has trivial outer automorphism group. The split form, EVIII, which has maximal compact subgroup spin, fundamental group of order 2 and has trivial outer automorphism group. EIX, which has maximal compact subgroup E7 times SU, fundamental group of order 2 and has trivial outer automorphism group. For a complete list of real forms of simple Lie algebras, see the list of simple Lie groups. E8 is an algebraic group. By means of a Chevalier basis for the Lie algebra, one can define E8 as a linear algebraic group over the integers and, consequently, over any commutative ring and in particular over any field. This defines the so-called split form of E8. Over an algebraically closed field, this is the only form. However, over other fields, there are often many other forms, or twists, of E8, which are classified in the general framework of Galois cohomology by the set H1, which, because the Dynkin diagram of E8 has no automorphisms, coincides with H1 over R. The real connected component of the identity of these algebraically twisted forms of E8 coincide with the three real Lie groups mentioned above, but with a subtlety concerning the fundamental group. All forms of E8 are simply connected in the sense of algebraic geometry. meaning that they admit no non-trivial algebraic coverings. The non-compact and simply connected real Lie group forms of V8 are therefore not algebraic and admit no faithful finite-dimensional representations over finite fields. The Lang-Steinberg theorem implies that H1 equals 0, meaning that T8 has no twisted forms. See below. Representation theory. The dimensions of the smallest irreducible representations are 1, 248, 3875, 27,000, 30,380, 147,250, 779,247, 1,763,125, 2,450,240, 4,096,000, 4,881,384, 6,696,000, 26,411,008, 70,680,000, 76,271,625, 79,143,000, 146,325,270. 203,205,000, 281,545,875, 301,694,976, 344,452,500, 820,260,000, 1,094,951,000, 2,172,667,860, 2,275,896,000, 2,642,777,280, 2,903,770,000, 3,929,713,760, 4,076,399,250, 4,825,673,125, 6,899,079,264, 8,634,368,000, 12,692,520,960. The 248-dimensional representation is the adjoint representation. There are two non-isomorphic irreducible representations of dimension 8,634,368,000. The fundamental representations are those with dimensions 3,875, 6,696,000, 6,899,079,264, 146,325,270, 2,450,240, 30,380, 248 and 147,250. The coefficients of the character formulas for infinite-dimensional irreducible representations of V8 depend on some large square matrices consisting of polynomials. The Lustig-Vogel polynomials, an analog of Cartan-Lustig polynomials introduced for reductive groups in general by George Lustig and David Cartan. The values at one of the Lustig-Vogel polynomials give the coefficients of the matrices relating the standard representations with the irreducible representations. These matrices were computed after 4 years of collaboration by a group of 18 mathematicians and computer scientists, led by Jeffrey Adams, with much of the programming done by Foucault Duclos. The most difficult case is the split real form of V8, where the largest matrix is of size 453,060 times 453,060. The Lustig-Vogel polynomials for all other exceptional simple groups have been known for some time. The calculation for the split form of E8 is far longer than any other case. The announcement of the result in March 2007 received extraordinary attention from the media, to the surprise of the mathematicians working on it. The representations of the E8 groups over finite fields are given by Deligne-Lustig theory. Constructions. One can construct the E8 group as the automorphism group of the corresponding E8 Lie algebra. This algebra has a 120-dimensional subalgebra so generated by Jij as well as 128 new generators Qa that transform as a Weyl Majorana spin or of spin. These statements determine the commutators as well as while the remaining commutator is defined as, it is then possible to check that the Jacobi identity is satisfied. Geometry. The compact real form of E8 is the isometry group of the 128-dimensional exceptional compact Riemannian symmetric space EVIII. It is known informally as the octo-octonionic projective plane, because it can be built using an algebra that is the tensor product of the octonions with themselves, and is also known as a Rosenfeld projective plane, though it does not obey the usual axioms of a projective plane. This can be seen systematically using a construction known as the magic square, due to Hans Freudenthal and Jacques Tits. E8 root system. A root system of rank R is a particular finite configuration of vectors, called roots, which span an R-dimensional Euclidean space and satisfy certain geometrical properties. In particular, the root system must be invariant under reflection through the hyperplane perpendicular to any root. The E8 root system is a rank 8 root system containing 240 root vectors spanning R8. It is irreducible in the sense that it cannot be built from root systems of smaller rank. All the root vectors in E8 have the same length. It is convenient for a number of purposes to normalize them to have length square root 2. These 240 vectors are the vertices of a semi-regular polytope discovered by Thorold Gosset in 1900, sometimes known as the 421 polytope. Construction in the so-called even coordinates system. E8 is given as the set of all vectors in R8 with length squared equal to 2 such that coordinates are either all integers or all half-integers and the sum of the coordinates is even. Explicitly, there are 112 roots with integer entries obtained from by taking an arbitrary combination of signs and an arbitrary permutation of coordinates, and 128 roots with half-integer entries obtained from by taking an even number of minus signs. There are 240 roots in all. The 112 roots with integer entries form a D8 root system. The E8 root system also contains a copy of A8 as well as E6 and E7. In the odd coordinates system, E8 is given by taking the roots in the even coordinates system and changing the sign of any one coordinate. The roots with integer entries are the same while those with half-integer entries have an odd number of minus signs rather than an even number. Dynkin diagram. The Dynkin diagram for E8 is given by. This diagram gives a concise visual summary of the root structure. Each node of this diagram represents a simple root. A line joining two simple roots indicates that they are at an angle of 120 degrees to each other. Two simple roots which are not joined by a line are orthogonal. Carton matrix. The Carton matrix of a rank R root system is an R times R matrix whose entries are derived from the simple roots. Specifically, the entries of the Carton matrix are given by whereas the Euclidean inner product and alpha I are the simple roots. The entries are independent of the choice of simple roots. The Cartan matrix for E8 is given by the determinant of this matrix is equal to 1. Simple roots. A set of simple roots for a root system phi is a set of roots that form a basis for the Euclidean space spanned by phi with the special property that each root has components with respect to this basis that are either all non-negative or all non-positive. Given the E8 Carton matrix and a Dynkin diagram node ordering of 1, choice of simple roots is given by the rows of the following matrix. Weyl Group. The Weyl Group of E8 is of order 696,729,600, and can be described as O plus 8. It is of the form 2G2, where G is the unique simple group of order 174,182,400. E8 root lattice. The integral span of the E8 root system forms a lattice in R8 naturally called the E8 root lattice. This lattice is rather remarkable in that it is the only even, unimodular lattice with rank less than 16. Simple subalgebras of E8. The Lie algebra E8 contains as subalgebras all the exceptional Lie algebras as well as many other important Lie algebras in mathematics and physics. The height of the Lie algebra on the diagram approximately corresponds to the rank of the algebra. A line from an algebra down to a lower algebra indicates that the lower algebra is a subalgebra of the higher algebra. Chevalier groups of type E8. Chevalier showed that the points of the algebraic group E8 over a finite field with Q elements form a finite Chevalier group. Its number of elements is given by the formula. The first term in this sequence, the order of V8, namely 3.38 times 10^74, is already larger than the size of the monster group. This group E8 is the last one described in the Atlas of Finite Groups. The Shaw multiplier of E8 is trivial, and its outer automorphism group is that of field automorphisms. Lustig described the unipotent representations of finite groups of type E8. Subgroups. The smaller exceptional groups E7 and E6 sit inside E8. In the compact group, both E7 times SU and E6 times SU are maximal subgroups of E8. The 248-dimensional adjoint representation of E8 may be considered in terms of its restricted representation to the first of these subgroups. It transforms under E7 times SU as a sum of tensor product representations, which may be labeled as a pair of dimensions as plus representations. Since the adjoint representation can be described by the roots together with the generators in the Cartan subalgebra, we may see that decomposition by looking at these. In this description, consists of the roots, and the Cartan generator corresponding to the last dimension. Consists of all roots with or in the last two dimensions, together with the Cartan generators corresponding to the first 7 dimensions. Consists of all roots with permutations of or in the last 2 dimensions. The 248-dimensional adjoint representation of E8, when similarly restricted, transforms under E6 times SU as plus. We may again see the decomposition by looking at the roots together with the generators in the Cartan subalgebra. In this description, consists of the roots with permutations of in the last 3 dimensions, together with the Cartan generator corresponding to the last 2 dimensions. Consists of all roots with or in the last 3 dimensions, together with the Cartan generators corresponding to the first 6 dimensions. Consists of all roots with permutations of or in the last 3 dimensions. Consists of all roots with permutations of or in the last 3 dimensions. The finite quasi-simple groups that can embed in E8 were found by Gries and Reiber. The Dempwolff group is a subgroup of E8. It is contained in the Thompson sporadic group, which acts on the underlying vector space of the Lie group E8 but does not preserve the Lie bracket. The Thompson group fixes a lattice and does preserve the Lie bracket of this lattice mod 3, giving an embedding of the Thompson group into E8. Applications. The E8 Lie group has applications in theoretical physics and especially in string theory and supergravity. E8 times E8 is the gauge group of one of the two types of heterotic string and is one of two anomaly-free gauge groups that can be coupled to the n=1 supergravity in 10 dimensions. E8 is the U-duality group of supergravity on an 8 torus. One way to incorporate the standard model of particle physics into heterotic string theory is the symmetry breaking of E8 to its maximal subalgebra, SU times E6. In 1982, Michael Friedman used the E8 lattice to construct an example of a topological form manifold, the E8 manifold, which has no smooth structure. Anthony Garrett-Lissey's incomplete, an exceptionally simple theory of everything, attempts to describe all known fundamental interactions in physics is part of the E8 Lie algebra. R. Coldy, A. Tennant, and E. M. Wheeler al. reported an experiment where the electron spins of a cobalt niobium crystal exhibited, under certain conditions, two of the 8 peaks related to E8 that were predicted by Zamolodchikov.